Bismillahirrahmanirrahim. We have a wireless communication system with NT transmit antennas and a single receive antenna. The channel is represented by the row vector H of size 1 by NT. H is known to the transmitter. The transmit covariance matrix is sigma XX. The average receive signal to noise ratio is SNR. The objective is to maximize log to the base 2 of 1 plus the square root of SNR over NT, H sigma XX H Hermitian. The maximization problem is to be solved with per antenna peak power constraints. Element KK on the main diagonal of sigma XX must be less than or equal to PK. P1 all the way to PNT are given positive real numbers. The logarithm is a strictly increasing function. Maximizing the logarithm is equivalent to maximizing the quadratic form H sigma XX H Hermitian. The transmit covariance matrix is Hermitian and positive semi-definite, so this quadratic form is real valued and non-negative. It is equal to its absolute value. The quadratic form is a double sum K from 1 to NT, V from 1 to NT, HK, HV conjugate, sigma XX, KNV. Vector H has the elements H1, H2 all the way to HNT. Sigma XX KNV is element KNV in the transmit covariance matrix. Let's split the double sum into the terms in which the two indices are equal and the terms in which the two indices are distinct. So H sigma XX H Hermitian is equal to the absolute value of summation K from 1 to NT. When the indices K and V are equal, this becomes the magnitude of HK squared. This is multiplied by sigma XX of K and K. The other terms can be written in this form: summation K from 1 to NT minus 1, summation V from K plus 1 to NT, HK HV conjugate, sigma XX of K and V, plus the complex conjugate. So we add HK conjugate, HV, sigma XX of K and V conjugate. Note that this is sigma XX of V and K, as the covariance matrix is Hermitian. The main diagonal elements of the transmit covariance matrix are multiplied by those non-negative numbers known to the transmitter. To maximize this part, we set sigma XX of K and K equal to the maximum possible value PK. By the triangle inequality, the quadratic form is less than or equal to the magnitude of this part, which is summation K from 1 to NT, magnitude HK squared PK, plus the magnitude of this part. Applying the triangle inequality again to the double sum, the magnitude of this double sum is upper bounded by summation K from 1 to NT minus 1, summation V from K plus 1 to NT, the magnitude of HK HV conjugate, sigma XX of K and V, plus HK conjugate HV, sigma XX of K and V conjugate. Suppose that for every K in the set from 1 to NT, HK is the magnitude of HK e to the I phi K. Also assume that sigma XX of K and V is the magnitude times e to the I phi KV. This part here is equal to the magnitude of HK times the magnitude of HV times the magnitude of sigma XX of K and V. Then we have e to the I between brackets phi K minus phi V plus phi KV. We have another exponential that is exactly this but with a minus sign. This bracket is 2 cosine phi K minus phi V plus phi KV. To achieve this inequality with equality and to maximize the quadratic form, we make the argument of the cosine function equal to 0. In other words, phi KV is equal to phi V minus phi K. By doing this, the summand here becomes real valued and non-negative. What about the magnitude of sigma XX of K and V? Assuming that the transmitted signals are in vector X and that they are zero mean, then this sigma XX of K and V is the expectation of X of K X conjugate of V. By the Cauchy-Schwarz inequality, this magnitude is upper bounded by the square root of the expectation of the magnitude of X of K squared times the expectation of the magnitude of X of V squared. In other words, the magnitude of sigma XX of K and V is upper bounded by the square root of sigma XX of K and K times sigma XX of V and V. And we know that this is PK, that one is PV. Thus, the optimal sigma XX of K and V is equal to the square root of PK BV e to the I phi V minus phi K. This can be written as the square root times HV HK conjugate divided by the magnitudes. The optimal matrix is the rank 1 matrix UU Hermitian. U is a column vector of size NT by 1. The kth element in vector U is equal to the square root of BK HK conjugate over the magnitude of HK, the maximum value of the quadratic form, H sigma XX optimal, H Hermitian, is the double sum, summation K from 1 to NT, summation V from 1 to NT, square root PK, square root PV, magnitude HK, magnitude HV. This is achieved by making those cosines equal to 1. The maximum quadratic form can also be written as the square of summation K from 1 to NT, square root PK times the magnitude of HK.